We will conclude this session with a lesson on inverse trigonometric integrals. And essentially, we're going to learn to use the rules for differentiating inverse trig functions in reverse. The formulas that we need are these. So the integral of 1 over the square root of a squared minus u squared du is the arc sine of u over a plus c. And we just get it from the inverse rule for differentiating arc sine. Similarly, the integral of 1 over u squared plus a squared du is 1 over a arctangent of u over a plus c. And the integral of 1 over u times the square root of u squared minus a squared du is 1 over a arcsecant of absolute u over a plus c. Let's take a look at a proof of the second one. All of these proofs are effectively the same, so there's not much use in doing each of them, but I would like you to see where the ideas follow through with the second, because this is actually a great thing to understand when you go forward into Calc 2, if that is your if that's what you're interested in doing. So to prove this, suppose we want to find the integral of 1 over a squared plus u squared du. In order to do this, we're going to take advantage of some trigonometry. And it may not be obvious from the outset that this would lend itself to being solved using trigonometry, but I think it will make sense as we go through the process. Trigonometry, we have right triangles generally that we are working with. And of those right triangles, there are different sides that we can define. We usually have an observed angle theta, and based off of that observed angle theta, we can come up with other sides of the triangle. So, for instance, suppose I chose to let u be the function a tan theta. So in this particular case, I'm making this choice that u is equal to a tan theta. And knowing how I've decided that isn't important at this particular time. But just know that the process that I'm going to do will work out because I've chosen that. And these examples, you won't need to be able to choose based off of that. It's just something that it's a technique of integration that I know at this point that I'm using in order to work this out. So from here, just follow through how I solve it. That's what's important. Now, if I make this choice that u is equal to a tan theta, then what that means is the tangent of theta would have to be equal to u divided by a. And I know from trigonometry that tangent is the opposite side of a triangle divided by the adjacent side. So this side would be u, and this side could be a, and that would set up this relationship where the tangent of theta is u over a. And because this is a right triangle, I could actually solve for this remaining side if I just called it b, for instance. And to solve for that, I would say b squared is equal to u squared plus a squared, or b is the square root of u squared plus a squared. So I could replace b with the square root of u squared plus a squared. Once I have that, I can go back to my original problem and make some other substitutions that may not seem obvious to do on the outset, but again, this is going to work out, so just bear with me for the moment. So the original problem that I have, the integral of 1 over a squared plus u squared, contains a term which is similar to that square root that I just came up with. So let's consider doing this. Let's look at other sides of the triangle. Let's include a side that has that square root. So for instance, the cosine theta. So let's see what cosine theta is at this point. That we know is the adjacent side divided by the hypotenuse. And I have or I don't know why I put an h there. I have a squared plus u squared in the original problem. Over by the triangle I have u squared plus a squared. It's being added, so it doesn't really matter what order that's in. But I could say that cosine theta is a over this square root. Or equivalently, cosine squared theta would be a squared over a squared plus u squared. And that's really similar to what I have in my integrand, 1 over a squared plus u squared. It's just off by a squared. If I multiplied both sides by 1 over a squared at this point, the a squareds on this side would cancel, and 1 over a squared cosine squared is the same thing as what sits there in my integrand. So I can substitute 1 over a squared plus u squared with cosine squared theta divided by a squared. All right, that's a good change. That looks a little bit nicer than what we had originally. But I do have to have something to differentiate with respect to. So I can't just leave du because I no longer have u's in my problem. I have to change u, and du I have to change into d theta, which is my new variable. But in order to get du, what I can do is take the derivative of this original transformation. So if I let u be du, then du would be a, so the derivative of tangent is secant squared, so secant squared theta, d theta. So that means I can take du and replace it with a secant squared theta, d theta. So that's nice. And now I can do some simplification. So one of these factors of a can cancel out one of these factors, leaving me with just an a. So I have 1 over a on the outside of my integral because that's just a constant. But look what remains. Cosine squared times secant squared. Secant is the inverse of cosine. That whole thing cancels out. So I really just have 1 over a d theta, which evaluates to 1 over a times theta plus c, which sort of is an answer, but the problem is it's not the right variable. So I need my final answer to be in terms of the variable u instead of the variable theta. So then I have to come up with some means of determining what u is in terms of theta. Well, I did state right here that tangent of theta was u over a, and I can actually solve that for theta. I can say that theta is equal to the arctangent of u over a. So what this means is my integral is now 1 over a times the arctangent of u over a plus c. This proof is based on an integration technique that you will learn if you go into Calc 2. It's called trigonometric substitution. I think this is a great introduction to it, but as you solve problems from this section, you won't need to use this technique. All it does for us is establishes the rule. Now that that rule is established, we're free to use it, and it's probably best just to memorize the formulas that I gave you above. Because if you memorize these formulas, you don't need anything that I just showed you below. That's just a proof that these formulas work. So let's look at some examples. Starting with the integral of the square root of 1 minus 4x squared dx. So you have to decide which of the three forms it looks closest to. The arctangent is easiest to identify because it's the only one where your terms are added together. Here we have terms that are subtracted. If it's a constant minus a function, that's the form of the arcsine. If it's a function minus the constant, then it's the form of arcsecant. So we have to decide then what the values of u and a are, and just plug in. So for instance, I could say that this is the integral of 1 over the square root of 1 minus 2x quantity squared dx. And this is my constant, so a is equal to the square root of that, which is 1. Square root of 1 is still just 1. And u is 2x. Only thing that we have to be careful of when we go through our process of this is if u is just x squared, we don't have to worry about any constant multipliers. But if u is something different, then we might have to. So du can be written as, du can be written as 2dx. And therefore 1/2 du is equal to dx. So this becomes effectively the integral of 1 over the square root of 1 minus u squared times 1/2 du. And this is the exact form of the formula that we had for the arcsine function. You just have to pull the 1/2 outside. So what we're going to end up with is 1/2 arcsine, and it's u over a. So u is 2x, a is 1, so 2x over 1 is just 2x, and then plus c. So normally arcsine doesn't have a multiplier out front of it, but in this case there's a multiplier because of that du. So that's what you'll need to be able to do. Next here, the integral of 1 over x times the square root of 16x squared minus 3. So this is the form of the arcsecant, and what's happening here is my function u is the function that's squared underneath there. So u is going to be the square root of 16x squared. A is the square root of that constant, so square root of 3 in this case. And then based off of u being 4x, we also have du as 4 dx, or 1/4 du is dx. So this will become 1/4 times the integral of 1 over x times the square root of u squared minus square root of 3 squared du, which is almost what we need. It's just that according to the formula, we need this part right here to also be the function u, not just x. It's a u, so whatever the u is defined by that 16x squared when we took the square root of it, square root of that gave us 4x. So I need a 4x out front here. Well, I'm in luck actually. In this particular example, I have a multiplier of 4, so I'm just going to put that inside. As such, now this thing is equal to u. So now I have the integral of 1 over u times the square root of u squared minus the square root of 3 squared du, and therefore, using the formula, it is 1 over the square root of 3, because it's 1 over a, arcsecant of the absolute value of u, so the absolute value of 4x, over a plus c. And there we have our answer. Now these can also work if we have different types of functions involved as well. So let me show you how that might occur. So I have two items in the denominator, both of which I could use as squares. One is a function, so I have to use that for u, so u would be sine x. And then a is a constant, so square root of 4 is 2. Also have to have a du, so du, alright, the derivative of sine is cosine, so cosine x dx. And let's see what happens when I substitute everything. So this becomes the integral. So 4 becomes 2 squared. Sine squared x becomes u squared. So it's effectively a squared plus u squared. Dx becomes cosine x dx. So that get exchanged with u, and I have the cosine x in the numerator times dx, so all of that gets exchanged with du. And this turns right into the form for arctangent. So the rule for arctangent is that it's 1 over a, so 1/2 arctangent of u over a, u being sine x in this case, plus c. And it's possible that the arctangent of sine over 2 could be simplified in some way. It's not going to be necessary at this point, as long as you can show proficiency with the rules surrounding what we're trying to test on here, which is the arctangent rule, the arcsine, arcsecant, arcsine rules for integration. Now, there's another situation that you run into and need to be able to integrate. So the integral of 1 over x squared plus 4x plus 9. So I have two squares in the denominator. I have the x squared and I have the 9. But I have this complicating thing, which is the 4x. The problem with that 4x is it prevents me from having the sum of two perfect squares in the denominator. But there's this process that everybody rolls their eyes at, but is one of the most important processes in algebra, completing the square. It can take a non-perfect square trinomial and change it into a perfect square trinomial. The way we would do it is this. We would separate the constant from the rest of the terms. Now, the value multiplying x is 4. If I divide it by 2, that gives me 4, and then if I square that, that's 4. So x squared plus 4x plus 4 is a perfect square trinomial. But I can't just get away with adding 4 in a problem without also doing the inverse, which is to subtract 4 somewhere else. So x squared plus 4x plus 4 factors into x plus 2 quantity squared. 9 minus 4 is 5. So this is completely equivalent to the integral of 1 over x plus 5 quantity squared, x plus 2 quantity squared plus 5. And I have my dx on the outside. now I have two things that 5 isn't technically a perfect square, but it's okay. I can use the square root of 5 here in this next stage. But I've got a function that's a perfect square, and that's the most important part, because now what I can do is let u be the x plus 2, a is the square root of 5, du is just dx at this point. So this changes into the integral of 1 over u squared plus, if a is the square root of 5, I could call this a squared du, and that's exactly the form that I want for my arctangent rule. So this becomes, for arctangent, 1 over a, so 1 over the square root of 5, arctangent of u over a, so x plus 2 over root 5 plus c. And last, let's do an example that uses a definite integral. All right, so to evaluate this as a definite integral, I'm going to change the variable, so I have to do the endpoints as well. All right, so here, one thing to note is that e to the negative 2x power is the same thing as, let's say, e to the negative x squared. Because if you simplify exponents and you have some base raised to an exponent and then raised to another exponent, you simplify by multiplying your exponents. So this can be written as a perfect square, which tells me what u is going to be. U is going to be e to the negative x. Then du would be the derivative of this, which would be negative e to the negative x dx. A, if you'll notice, a here is just the constant 1, so that's rather nice here. And the thing is, I don't exactly have an e to the negative x. I don't have a negative e to the negative x in the numerator, I just have e to the negative x. But I can put a negative here and a negative on the outside, or I can divide that negative over to the du part. Either way, I'm going to have a negative after I do my substitution. So negative, I'll handle the endpoints in a second. Negative e to the x dx, all of that gets replaced with du. In the denominator, it's 1 minus, and then e to the negative 2x is same thing as u squared. The endpoints, whenever you change the variable of integration, you also have to change the endpoints of integration. So the original endpoints of integration are functions of x. What we need to do is change those into u's by plugging them into our transformation function. So u of 0 would be e to the negative 0, or just e to the 0, which is 1. So this lower endpoint now is 1. U of natural log 2 would be e to the negative natural log 2, and I think we can do a little bit with that and make it a little bit nicer. So for instance, this could be e to the, when you have a number multiplying a logarithm, you can make that an exponent on the argument of your logarithm. So I can make that e to the natural log of 2 to the negative first power. E raised to a log base e, those things cancel each other out. So this actually just results with 2 to the negative first power, or 1/2. So this upper endpoint is just 1/2. And we could probably make that a little bit nicer by getting rid of this negative out front. Since the lower endpoint is larger than the upper endpoint, let's just swap those and make it from positive integral from 1/2 to 1 of 1 over the square root of 1 minus u squared du. Okay, now we need to evaluate. So this is of the form of arc sine. So this would be arc sine. So arc sine doesn't have the 1 over a like the other two do. So arc sine of u over a. So u over, and a is 1, so actually let's just write that as u. Arc sine of u evaluated from 1/2 to 1. And I'll come down here and say that is arc sine of 1 minus the arc sine of 1/2 and to evaluate these, you just have to think about your inverse trig functions, and it's probably been a while, and that's fine. Effectively, we're looking for the angle for which the sine function is equal to 1. So the angle for which the sine function is 1, that is pi over 2. So sine of pi over 2 equals 1, so the arc sine of 1 is pi over 2. Similar argument for arc sine of 1/2. So we're looking for the angle measure for which sine is equal to 1/2. So sine is equal to 1/2 at pi over 6. So pi over 2 minus pi over 6 is the same thing as 3 pi over 6 minus pi over 6, which is 2 pi over 6, or pi over 3 is my area underneath this particular curve.